Good afternoon, everyone. I'm going to talk about the automated verification of the soundness of DNN certifiers. In other words, we are trying to ask the question, can you verify the verifiers? This work is done in collaboration with Yasmin, Charith, and Gagandeep at UIUC. So we have seen in the past that AI is unreliable. There have been several instances of car crashes with self-driving cars, and a lot of the AI models are embarrassingly non-robust to even small perturbations. To deploy these models to safety-critical domains, we need better guarantees. Currently, most of the guarantees are based on metrics like accuracy, precision, recall, but they are not enough to build trust in neural networks. For example, it's easy to fool a neural network to misclassify this as a speed limit sign instead of a stop sign. The kind of properties that we want to verify usually involve a set of images or a set of inputs, which are usually infinite. Several ways have been developed to gain reliability in neural networks. The first one, on one extreme, is a testing technique where you sample a bunch of inputs from the input region, and you test the outputs against the property. Now, this is scalable, but this is unsound technique. On the other end of the extreme, we have solvers like SMT solvers or MILF solvers. Now, these are sound. In several cases, they are also complete, but they do not scale. In the middle, we have abstract interpretation-based certifiers. These are sound. They are mostly not complete, but they offer a knob where you can vary the precision and scalability trade-offs. So they offer the perfect solution for neural network verification, and this is also the topic for our research. Abstract interpretation-based certifiers are based on the key idea of over-approximation. So let's say you want to certify the property on a set of images, which is represented by phi here. Now, we abstract out that using some abstraction function, which is alpha of phi, and it is represented using the blue region, which is the over-approximation of the actual set. Now, instead of propagating the actual images through the neural network, this blue over-approximation is propagated through the neural network. But the key thing is that at every layer, at every step, it must be an over-approximation. So finally, at the final layer, we get an over-approximated output. Now, if this output satisfies the property, then we can say the original images also satisfy the property. Now, this over-approximation is important to ensure the soundness of the certifiers. But other things that the developer needs to care about is the precision and the scalability. If it is too precise, it may not be scalable. If it is very scalable, it may not be too precise. So they need to maintain the balance. So everything is so good so far. But the problem really starts when you have to develop one, actually, because the development process is very tedious. It usually starts with an application. The first step is to come up with a mathematical design of the certifier. This involves coming up with an abstract domain, abstract element, abstract transformers, maintaining their soundness, maintaining their precision and scalability. The second step is going and writing long pen and paper proofs which prove that every transformer is an over-approximation of the actual concrete operation. And the third step is the implementation. Now, those in the audience who actually do neural network verification, they will realize this pain, that coming up with the design of a neural network verifier and actually implementing them are two completely different ball games. Because the granularity at which they are designed is at the neuron in a neural network, that what each neuron is supposed to do. But when they're implemented, neural networks are layers, so they have to be implemented on tensor level. So it's a completely different thing. We provide an alternate approach, where instead of coming up with pen and paper designs, they write in a DSL, which we call constraint flow, because it's basically the constraints which are flowing through the neural network. Once we have a specification in constraint flow, we can automatically verify the correctness of this specification. From correctness, I mean the over-approximation based soundness. Now, you no longer need to write the pen and paper proof. That can be done automatically. And once that is done, we have a compiler which can compile those specifications into an actual executable that run on neural networks. Now, be it CPU backend or a GPU backend, you will get it for free. Constraint flow DSL was introduced at last SAS in 2024, and this work is presenting proof sound, which is OOPSLA'25. Let's look at some example certifiers before we go on. The first one, very commonly used, it is the interval bound propagation. It associates two bounds with each neuron in the neural network. So a neural network, I'm considering a graph where the vertices are called as the neurons. So with each neuron, IBP associates two bounds, a lower bound and an upper bound. And the constraint is L is less than equal to N is less than equal to U. We have another very popularly used certifier, which is deep poly. Instead of two bounds, it associates four things. Small l, small u, same as the previous one. but a capital L, capital U, which are the lower and upper polyhedral bounds this time. And the constraints are similar. L is less than equal to N, less than equal to U. Now, these fields that are associated with the neurons are what we refer to as the abstract shapes. And the abstract element is the conjunction of the abstract shapes of all the neurons in the neural network. That's one abstract element. And the constraints, they define the over-approximation-based soundness. So this is the constraint that they want to maintain at each layer. So that is the over-approximation-based property, which I'll refer to as P in the next slides. Now, in constraint flow, these algorithms can be written in just tens of lines of code, as opposed to 10,000s of lines of code in their standard implementation. How? They just need to first write the abstract domain, which I just showed you what it is, along with the over-approximation-based soundness property. Notice the polyhedral expressions. So these are very commonly used in neural networks. They are amongst others. So we provide them as first-class citizens so that users don't have to write much. The second, they define some user-defined functions which help them write the abstract transformer. They are declarative, loop-free, pointer-free, so everything is good for verification. And finally, they write the abstract transformers corresponding to all the operations in the neural network. Affine here represents a fully connected layer and a convolution layer, but users have to write it for ReLU, sigmoid, or whatever activations there are in the neural network. That's all. What do we mean by the soundness of the certifier? Let's assume there is a concrete domain and an abstract domain. Abstract element has been defined, let's assume. And let's say we are given an abstract element A. We also know that this abstract element over-approximates a concrete element C. Now we apply a concrete function to the concrete element and an abstract transformer to the abstract element. What we want to ensure is that the abstract element still over-approximates the concrete element even after the application of the function. But we want to ensure this for all possible abstract elements and concrete elements. Now, notice this for all quantification. This for all quantification induces a for all quantification over all the neural networks. Why? Because A is a conjunction of abstract shapes of all the neurons in the neural network. Now, if we want to verify the soundness of a certifier, we want it to be agnostic of the DNN. DNN is an input to a DNN certifier. But I don't have a way to represent all possible DNNs. Think about Z3. Is there a way to write all possible DNNs? There's not a direct way. So that is the key challenge that we try to address. Now, before going on to the solution, let's take a concrete example. I've slightly modified the depoly algorithm to show the intricacies of the solution. Let's take the ReLU activation. So from current, I mean a neuron in the current layer. Previous is a neuron in the previous layer. So current is equal to the ReLU of previous. Treat them both as neurons, not as layers. Usually, ReLU is specified in 3 cases. The first one, when both the bounds of previous are in the positive region. Second, when they're positive and negative. And the third, when both are negative. Let's take the first case. In the first case, ReLU almost behaves like an identity function. So the lower bound, upper bound, lower polyhedral bound, all can be set to the corresponding bounds of the previous. But for the upper bound, we made a slight change. We did previous u dot map replace upper. Let's look at what exactly this is doing. Let's say E is a polyhedral expression, 5n1 plus 6n2 minus n3. Polyhedral expression is simple affine function over the neurons. And replace upper is a function that takes in a coefficient, which is a real number, and a neuron. And based on the sign of the coefficient, it either outputs n of u or n of l, upper bound or the lower bound. Basic idea is we want to get an upper bound based on the sign, upper bound of c into n. So this map construct now applies this function f to all the sum ends of E. So basically E dot map, it's very similar to MapReduce. So it gives us f of 5, n1 plus f of 6, n2 minus f of 1, n3. So similarly, we apply E dot map replace upper, we get this expression. The basic idea is we want some upper bound of E. OK, so keep this running example in mind. Now to do formal verification, we first come up with the formal semantics of constraint flow. Now we come up with the operational semantics where the input to the DNN certifier, again, please remember, is a DNN. But when we want to verify the correctness of a verifier, we don't want it to be restricted to one DNN. It has to be correct for all DNNs. So there has to be some notion of a symbolic DNN. And once you have a symbolic DNN into picture, the operational semantics no more apply. So we come up with symbolic semantics, where you have a symbolic DNN, apply the symbolic semantics, and now you can do some verification. Let's look at the concrete solution. The first step is to create a symbolic DNN, which starts with just 2 neurons, which are previous and current. Both of them will be associated with their own abstract shapes, which are L, U, capital L, capital U. Now we initialize all of these entities with symbolic variables, one per each. But now if you notice, we initialize this U with a single symbolic variable. How do we apply map? So we need some expanded form of this U. So we do the symbolic DNN expansion, where we replace this one symbolic variable with a full polyhedral symbolic variable. But in order to do so, notice that we introduced 2 more neurons. So we need to introduce that in the symbolic DNN. And they will also be associated with their own abstract shapes. So now this is the full expansion in order to symbolically execute the given expression. Once we have the fully expanded symbolic DNN, now we have the given conditions that the property was already true for previous N1 and N2. And what we want to verify is that the property still holds on current after the application of the transformer. We also assume that current is ReLU of previous. And this can be offloaded to an SMT solver. Coming back to the formalism, now how do we prove that this is whatever we are doing is correct? So we come up with the notion of symbolic semantics over approximating operational semantics, and a symbolic DNN over approximating several concrete DNNs. Now this notion gives us the result that if you prove the correctness on a symbolic DNN, this automatically implies the correctness on all concrete DNNs. But take into consideration the bounded verification. I've not introduced, but there are bounds. And this is 80-page long appendix. For evaluation, we took several certifiers and their corresponding abstract transformers. Most of the verification can be done within 1 to 2 seconds. And we also introduced new abstract transformers and certifiers. So this also shows the utility of constraint flow, that's easy to develop new and verify new certifiers and verify them. To conclude, the whole objective of this work is to reduce the manual effort and increase automation as much as possible. We want to democratize neural network verification and make it available to more and more users. So we introduced a constraint flow spec where you can just write the certifiers in a few lines of code. ProveSound takes it, checks it for over approximation-based soundness. If not, you need to come up with a better specification. If it does, it passes on to the compiler, which gives us the final executable. It also allows several future directions. The first one, our current support for the compiler, which we have not discussed yet, but is only for the CPU. We want to extend it to a GPU backend. 2, very interesting, that now since we have all the basic recipes, we also want to extend it to language model certifications and check if that is possible or not. Third, what if we include all of this verification process within the training of neural networks? So this is called certified training, and we also want to support it through constraint flow. Finally, what we are exploring is certifier synthesis. We have all the basic recipes if you see. We have a DSL, we have a checker, we have a compiler. So why not automatically synthesize the transformers for a particular application? So that's also what we are exploring. And there are other future directions possible. I'm happy to take questions now.
We have time for one question, just one.
I wonder, have you applied your toolchain, the certifier, to real DNNs?
We have applied it to
and what's
standard.
the performance behaviors?
We have applied it to the standard benchmarks. It works very well. So it will show up in the upcoming paper for the compiler. But the current version is only testing the correctness of a certifier. It is not applying it.
But the certifier yourself, have you applied the certifier yourself?
Yes, yes, it works well.
To benchmarks?
Yes.
OK, thank you.
Let's thank the speaker again.